So good morning, all of you. Last time we have seen these three different cases of damp-free vibration cases, and also we have found out the displacement of damp-free vibration in all these three cases. Also, we have seen the applications of over damp-free vibration, under damp-free vibration cases, where you can actually apply those equations for which type of structures, which type of uh, other applications, like you can say overburden, overdamp vibration system you can apply for shock absorbers, door dampers, many other equipments, galvanometers like that. We have seen combined effect of all these three cases. This is the response of damp-free vibration, in which the critical damping, over damping, and under damping is been plotted on a single graph so that you can actually compare the response of each other. Now let us see the example based upon this, so that you will be understanding how to actually use those things. Derive the equation of motion for small rotation of rigid uniform mass of 12 kg is shown in the figure, right? Take K is equal to 2500 Newton per meter, C is equal to 8 kg per second, and what is the damping ratio? That is, you need to find out first. If the rotation of 0.1 degree at point A is applied and the bar is being released, compute the displacement at end D after 3 seconds. So that is your second questions. So here, what is the new thing that has been coming up in this particular example, what we have not seen earlier? That is, now it is the rigid uniform beam of mass 12 kg, means this mass 12 kg is uniformly distributed, and which is the weight of this particular beam. So previously we might not have considered this particular thing, which is having a self weight. I think we have done one example, we have taken one example to address this, but this is the exclusive examples in which you can take the self weight of the beam, which has been given 12 kg. You can see this beam here is the spring is being given. You can see here. So the spring is given, and this is a spring, and this is the damper is being given. Value of K and value of C is also being given, right? Let's see now. So first, what I need to do is, first I need to draw the free body diagram of this. So let us draw the free body diagram. It is the hinge has been given. You can see from here. So the hinge is given. So I am drawing the hinge, and then this particular beam. Okay. So this beam is having my length L. So this is my length L, correct? Okay. Now, when this particular beam is subjected to rotation, so this is my direction of rotation, right? This is my direction of rotation. And so that this beam will rotate to an angle which is theta from the point A. So as it is moving in this direction, definitely here the spring is being attached, and here is the damper is being attached, so that the spring force will act in an opposite direction. So here is the spring force will act, right? The spring is being attached at a distance A from this particular end. You can see here 2 meter is given, which is nothing but the distance A. Am I right? So A is given. Second, the second force which will going to act as this, that is this force, which is FD force, which is a damping force, which will be acting at a distance L from point A. And third point, which is the inertia force, which will be going to act at the midpoint of this, means at a distance of L by 2 from here. So this is a distance L by 2 from here, and this force is going to act here. So that is the Fi force. Am I right? since this particular lamina is going to take the moment in this direction, because one is the hinge, and if you are applying the force from here, so the moment inertia is also going to act at the same point. So since the moment is in the clockwise direction, the inertial moment will act in the opposite direction to this. This inertial moment will come into the effect if I'm considering the self weight of the beam. That is what we have seen earlier. If the self weight I'm not considering, in this case, this particular inertial moment will not come, right? Only the Fi will come. But since I'm considering the self weight, my inertia forces I need to consider in this way. So the inertia forces is the combination of Fi plus Mi. Now let us see how we can actually calculate all these forces. So let us find out each and every force. So first let us find out inertia force Fi. So the Fi is equal to, as per definition, Fi is equal to m into double derivative of displacement of the mass. Again I am repeating, Fi is equal to m into double derivative of displacement of the mass. So the mass is acting at the centroid of this particular beam, which is acting L by 2 from here. So the total displacement at this point will be L by 2 into this theta. So that is the displacement. So m into L by 2 into theta double dot, if I take, then it is a double derivative. So my Fi will be this. Similarly, I need to calculate the mass moment of inertia or the moment inertia Mi. So if you see the lamina which is having a length L and the mass M, then the mass moment of inertia for such cases you can see from any applied mechanics book, which is ml square upon 12. This is the formula for mass moment of inertia if the beam is having length L and mass M into theta double dot. So this will give you the Mi. Now if you want to find out the total inertia which is being transferred to this end, so means that is the Mi star. I'm supposed to say it is a Mi star, which is the combination of this and this. So basically Mi star is nothing but it is the Fi plus Mi. I'm doing it. So if you do Fi plus Mi, then you will get this particular ml square by 12 plus ml by 2, right? You can see here. Then this particular formula will comes into the effect. Okay, basically you need to take, you can see the area of this. So this is your Mi. I'm transferring here. So this will be ml square by 12. You can see this ml square by 12, which is acting at the distance of L by 2. So 2 by L, right? So ml square by 3 will comes into the picture. We have seen earlier also these cases. You can actually refer to this. So this will be ml square by 3, right? Now, if you see other formulas, which is FD and FS. So FD you can calculate with, as per definition, is the C into single derivative of displacement of the damper. Here the damper is being placed here. So the total displacement will be L into theta. So that is the displacement of the damper. So C into L theta will come. So that is this, the value of FD. Similarly, if you want to calculate Fs, so it is K into displacement of spring, which is K into A theta, because this length is A and this displacement of the spring will be A theta. So if I put this all the value, Mi you have calculated ml square by 3 into theta double dot plus C into L theta into L plus K into, how this formula is coming? This formula has been coming by taking the M. Or what you can do is straight away, if you do not want to calculate this, for example, let us not calculate this. Okay. What you do is you keep mi and fi as it is in the formula. Okay. So if you put it in here, and if I'm taking directly the moment at point A, okay, then what will come? See, I'm writing here again. First, fi into L, this distance, which is L by 2, right? Fi into L by 2. Am I right? Plus, I'm taking, you can say this anti-clockwise moment as positive. So Fi into L by 2 plus, directly this is a moment, anti-clockwise moment. So I need to put it as it is. So this moment will be, we have calculated is ml square by 12 into theta double dot. Okay. So I will say it is nothing but it is mi. Directly I'm putting whatever the value is there. So mi plus this 2 will be coming fd into L, right? And fs, which is this fs into A, which is equals to 0, right? fd into L plus fs into A, which is equals to 0. Now put this value of fi here. Fi we have calculated is, you can say m into L by 2 into theta double dot. So m into L by 2, right, into theta double dot, and this L by 2 is there. So this will be L square by 4. Am I right? Plus ml square, this value we have calculated, ml square by 12, I'm talking about this, into theta double dot. And the rest of the thing is this from here, right? You can see this. Plus, I'm not writing this, plus assume, you can say this value of FD you put it and FS you put it, you will get this. Now if you see this, this is ml square by 4, this is ml square by 12. So if you take theta double dot out, then this will be coming ml square by 3. That is what has been written here. You can see this. If I solve this 2, then this will be coming. Okay. And then the rest will be same. So if you now plot in terms of this, that is ml square by 3 into theta double dot, plus here you can take CL square into theta dot plus K into A square into theta is equal to 0. If you see this formula, which comes into this particular form of this formula, which is m star plus c star plus k star is equal to 0, then m star is nothing but this, c star is nothing but this, k star is nothing but this. You have all this value. You have the value of m, which is given 12 kg. L is given, which is 5, 2 plus 3, right? Here is given 2 plus 3, so 5. Then all this parameter is known to you. Okay, C value is also given, L value is also given, K value is also given, A value is also given. So you can easily calculate what will be the value of M star in numerical, C star in numerical, and the K star in numerical. Once you find out, first you need to find out the, as you see, this is the 0 here. So it is a free vibration case, and also there is a damping is also given. So there is a damp free vibration case because the value of C is also been coming, right? So this is the case of damp free vibration. Now first to calculate, you can say the first answer is you need to find out the damping ratio, right? Now to calculate the damping ratio, first you need to find out is omega, which is K star upon M star. If you calculate the K star upon M star, this values, then this value will come around 10 radian per seconds. Now, you know this particular formula we have defined. You can see this formula while we are taking this. So C star is equal to 2 eta omega m star. Here the C star and m star I am putting it. So you can easily calculate. You can see the value of C star. You have the value of C star here. 2 omega is also you have calculated. M star value also you have. Just what you need to find out is you need to find out the value of eta, which is nothing but your damping ratio. If you calculate this damping ratio by putting those numericals, then this value is coming 0.1. And as you know, if your eta value is less than 1, then you can say this is the underdamped free vibration case. Am I right? So this is your first answer, and from this you can say that it is my underdamped free vibration case. So once you know this, it is the underdamped free vibration case, you can use the formula for underdamped free vibration case as well as the frequency. And as you know that underdamped frequency is omega d, and we have defined omega d is omega under root of 1 minus eta square. So my underdamped frequency is 9.95. If you put the value of omega, which is 10 radian per seconds, eta is equal to 0.1 into this. So that is 1. Now I'm going to find out the another answer, that is if the initial rotation of 0.1 radian is applied at point A and the bar is released, compute the displacement at T. So I am going to apply the initial rotation here, which is of 0.1 radian, and I need to compute the displacement of this bar when it is started vibrating after 3 seconds, right? So first what I'm trying to find out is, first let us find out the displacement of this. So as you know, it is an underdamped free vibration case, right? So the equation of displacement you can put in terms of theta. We have established this particular equation in terms of x of t. Here I am putting, in place of x, I am putting the displacement, which is theta into t, which is nothing but e raised to eta omega t into a cos omega dt plus b sin omega dt, where you have found out a is equal to x0. So here I am putting theta 0, and the b value you have calculated x0 dot plus eta omega x0 upon omega d, while we are solving this underdamped free vibration case. So this is basically the general form of underdamped free vibration case. Now see what are the values is available to you. In this eta you have already there 0.1. Time t you need to calculate after 3 seconds. So that is also you have. Value of omega is also you have, which is 10 radian per seconds. Omega d value, that is also you have. Initial rotation you have been given, so that is a 0.1 radian, that is also there, right? So if you take the derivative of this is a constant value, so theta 0 dot will be 0, that will come. Rest of the values you have here. So if you put theta at t is equal to 3 seconds in this formula and put all these values, then you will get the value which is, this is at point A, right? Theta at point A at t is equal to 3 seconds, which will be coming this, right? Which is in radian. But what you need to find out is, you need to find out at point D. And point D, what will be this displacement is L into whatever the displacement happen at theta, right? So theta into 8, this is what the displacement at time t. So basically you need to do L into theta. So here you have found out the displacement, which is minus 4.76, right? After 3 seconds. So whatever the value is coming here, multiplied by the length of this bar, 5 meter, which will give you the displacement at point t is equal to 3 seconds at, you can say, point D. You need to find out, you can say, this value, which is in radians or meter. Sorry, this will come in meter because radian I need to multiply with the meter, so it will be coming in the something meter. This minus sign represents the direction. If you are assuming the lower side will be the positive, probably at the time t is equal to 3 seconds, it may be in the upper side because it is vibrating like this, right? It may be up the zero line or it may be down the zero line. Since this value is minus, you can actually say that it is the reverse of our prediction if we are assuming positive sign for lower direction, right? Because my rotation is this way. So probably at the time of 3 seconds, it is in the upward direction of vibration. So this way, you can actually find out this second answer, which has been given in the example. I hope it is clear. If you have any questions, I may able to take on this and then go further. Okay. So if you do not have a question, let me take the second example, which is also relates to this. Now I'm increasing the difficulty level for a rigid uniform plate is shown in the figure number 1, which is this. Derive the equation of small oscillation first. So first of all, you need to derive the equation of small oscillation. So basically equation of vibration. Also find damping ratio of the system. Yes, you need to find out the value of eta. If initial rotation of 0.1 radian is applied at point A, means I'm considering point A is here. If you apply the initial rotation at point A, and if this plate has been released, then compute the displacement at point B, right, at the end of 5 seconds. It is same as what we have done in the previous example. But in this case also, we need to see in particular vibration case, first we need to establish the equation of motion. From this, we need to ascertain in which particular vibration this has been rotating. Once it has been known to us, then we need to find out what is the value of frequency corresponding to the natural frequency and for the particular vibrational frequency, and then we will actually put it into the general equation of displacement. Let us see that how to solve this. This plate, you can see this plate has been given, and on the point D side there is a spring has been attached to this, and on the lower side where point B is there is a damping value is also been, damper is also been attached. The value of C is given, value of K is also been given. This plate is having, this side is 3 meter, this is 2 meter, and also the mass of the plate is also required to be considered. So the inertial effect will also come into effect. Let's see now. So first let us try to draw this free body diagram of this. So let's see, this is what my initial plate is. So this is my initial plate. I am putting it, and this is placed at hinge here. So at point A, it is at the hinge. Now this plate is having a dimension. On this side, I'm supposed to say it is A, which is 3 meter, and B, which is this, which is 2 meter, this side. B, I'm supposed to say it is a 2 meter. Now, if I'm rotate this particular spring in this particular direction, then this is the new position at which this particular plate is been reaching. So this is rotating at an angle theta. Same angle will be seen over here also. Now, if you analyze this end is attached with the spring as the plate is moving on this side. So the spring force will act in this direction. So this is the spring force, right? And similarly, this plate is moving down. This is a damping force which will be act in this direction. Now you need to see what are the forces which will be considered as an inertia force. As the inertial force has been acting at the center or the centroid of the plate, the first inertia force due to the force which is acting Fi1, I am considering on this phase of this particular plate. Up till now, we have not taken the 2D objects. This is the first example in which I am taking the 2D object. So my inertia force, which will be in the combination of first, which is force which is acting on this phase. Second, the force, inertial force, which is acting on this phase because this end is going in this direction and lower end is going into this direction. So which will be resisted by Fi1 and Fi2. Also, this plate is subjected to rotational moment. So the moment which is resisting moment, which will be mi. So my total inertia force, which is the combination of this all three forces, right? Now, once you know this, first you need to find out the value of each and every one. So let us see what will be the value of Fs. So my Fs is here. So as per definition, it is K into displacement of the spring. So this is the length, which is B. So the displacement of the spring is B into theta. So this is the displacement of the spring, which is B into theta. So I am putting K into B theta. Then displacement of the damper, which is here. So this is my length A, and the displacement of the damper is this, which is A theta. So C into A theta, as per definition, it should be a dot. Now, if you put the value of K and B here, then this value coming 4000 theta. And if you put the value of C and A, then this value is coming 36 into theta. Now, these two forces I got. Now I need to find out these three forces together. So first, let us find out Fi1, which is nothing but mass into displacement of this force, which is perpendicular to the face of this angle. So Fi1, which is this, Fi1 will be this, right? So Fi1, am I right? So Fi1 is m into displacement, which is at the distance of this much. So I need to consider this displacement, so which is b by 2 into theta. So b by 2 into theta is this. You can see this, b by 2 into theta. Since as per definition it should be acceleration, so I'm putting double dot. So if you put m into b by 2, which is 10 into theta. Similarly, I need to find out Fi2. So if you say Fi2, which is this, so I need to consider, if I take, you can see this, so I need to find out this displacement, which is nothing but a by 2 into this theta angle. So a by 2 into theta. So m into a by 2 into theta, which is this. So if you put this all the value, which is coming 15 theta double dot, then you find out mi s. Again, you need to go back to your applied mechanics stuff, which is having, you can see the length a of this lamina and b, and which is subjected to mass m. Then this formula will be m by 12 a square plus b square and into theta double dot. Okay, so if you put this value, so 10 by 12, 3 square plus 2 square into theta double dot, this value coming 130 by 12 into this. If I take as per D'Alembert principle, considering the plate is in equilibrium, I will take, you can say the moment is equal to 0. And I will take, you can see the all these forces. So the first is, let's take the moment at point A here. Take the moment at point A here. So first, let us find out all these forces. So Fi1 into perpendicular distance from point A, which is b by 2, right? So Fi1 into b by 2, you can see this, Fi1 into b by 2. Then you will have Fi2 into perpendicular distance from A, which is a by 2, right? So Fi2 into a by 2, you can see this. And the third one is the moment, which I'm directly taking, since I'm taking moment, so mi. So I'm considering mi, which is here, plus fd into this length, which is a, fd into a, and I will take fs into this length, which is b, is equal to 0. So these are three is the term with the theta double dot. If you put this value 10, 15 plus 130, 10, 15 plus 130 by 12. So 130 by 12 plus 10 plus 15, this value you put it, okay, and also put the value of b and a. So this value, and take the outside this theta double dot. Similarly, put the value of fd and fs, put the value of a. So this will be this. Take it, you can say this three terms, theta outside, then you will get this term. Then this is the c terms. and this is your K term. If you relate this with the general equation of motion, you may able to get m star value, which is this, C star value, which is this, and K star value this. Since again it is a 0 here, so you can say that it is the free vibration. Also there is a C effect will also come, value of C is coming some value, so it is a damp free vibration case. So this is your first answer, that is the equation of motion. This other answer I'm leaving up to you, same way you need to solve as we have seen the previous example. First you need to calculate the value of omega, which is nothing but under root of K star upon m star. Calculate the value of omega, then you calculate the value of eta from the equation which is we have seen, which is omega eta. You can see this formula. Same way you need to go. C star is equal to 2 eta omega m star. Calculate the value of eta. See that whether it is coming less than 1, greater than 1, equal to 1. If it is coming less than 1, then it is under damped free vibration case, right? If it is coming over greater than 1, then it is over damped vibration case. Then calculate the value of omega d or omega d cap, this depending upon whether it is falling in under damped or over damped vibration case. Then corresponding equation of whatever the value of eta is being coming. Suppose eta is coming greater than 1. So in place of this equation, you need to use the equation for over damped. If it is coming same way, that is a less than 1, then you need to use the same equation and calculate the first at theta is equal to A at 5 seconds. And then it is transferred to point B, which is having a distance of B as per this particular formula. Multiplied with this length, you will get this particular value. So this way you can solve this particular example. I'm stopping here. I'm happy to take any questions if you have.